Thank you very much. So welcome everyone. My name is Pete Oliver Kruger. Really long last name, so some people just call me Pete OK. Makes it a lot faster. And I have a background in software development and architecture. And that's actually how I got started before I got into Agile coaching itself. And so I've been doing this stuff for quite a while. And sort of made my way up through doing architecture and then becoming a development manager before getting into the idea of having agile coaching. Along the way, I also had a fantastic idea for software. I'm building some software that people could buy and reuse. And so I started my own company for a little while until I discovered the difference between having a great idea and selling a great idea. And that led me to sort of introductions to lean startup and understanding the business side of things. And I became a product consultant, and long story short, that led me to doing a lot of coaching, especially in the agile space. And so normally I give talks about, transformations and agile sections, and about maybe the psychology side of how we interact together. But this time I wanted to give a presentation on some of the stuff that I haven't really touched a lot in a while, but it was still very relevant and still is stuff that I coach teams on, and that's how to restructure your code and really design it from the very beginning to be more sort of aware of Agile itself, of how we want to perform and act, as an Agile team. And having the right code structure can make all the difference in the world in being able to achieve some of the goals that we wish to do. I put it all together in what I used to call my pillars of Agile architecture. And there's about 5 different parts of this that we'll cover today. But first I want to give you sort of a little background and the reason why I even got to this place, or the reason why I think that this is relevant to your organizations and the places where you are. And a lot of it comes back down to this idea of the cost of maintenance, which is not something that we really tend to think about anymore. In the old school way, in the waterfall project, we had tracking for this stuff. Sometimes we had very completely separate teams, people who were doing new development and teams that were doing the maintenance development and fixing all of the bugs, and they were completely separated. And very much in the waterfall world, we had projects which were set out to build the initial application in that waterfall way, and then entire other projects that were set up afterwards to do the debugging or maintenance or add new features. And so in that time, in that world, it was really easy to separate out and start making calculations, and people were tracking things like how much of our budget was spent on new development and how much of our budget was spent on doing debugging and fixes and enhancements. And so we had some great metrics, for a while on where this breakdown was. And so if you were doing any kind of work with applications back then, you probably saw some of these statistics that got published on a regular basis. And it was shown through a bunch of different studies that maybe 60 to 80% of the work on any particular product out there was spent in maintenance and fixing bugs, creating enhancements, and adding to the application. And so we spend so much time trying to figure out applications and trying to figure out architectures and design those things when we first build it. And we spend very little time actually thinking about how much time we spend maintaining applications and how much time and the frustration that goes into fixing something when you discover halfway through the life of the product that you missed something, or you need to add a whole new feature, and that whole new feature could completely blow up the project. In the new sort of agile development process, we've got this place where everything is, just in the backlog. So we're sort of mixed all the stuff together. We've mixed the new development and maintenance in that backlog, and we're just tracking that all, and it's all just work. So in many ways, we kind of don't care about, is it new development or is it maintenance? And it really shouldn't make a difference as far as prioritization. It's all stuff that our customer needs. It's all stuff that needs to be built. But it does matter when it comes to architecture, and it does matter when it comes to being able to make quick fixes to things, or be able to handle those production bugs when they pop up, or really just being able to make changes in the product maybe 5 years into the product timeline, which is not something we usually think about. And there's kind of the symptoms of this that you'll see in a bunch of organizations is I still run into organizations where there are maintenance teams. There are entire teams of people that their job is just to take an existing product and to do the fixes on those and to add additional features on top of those pieces that are already there. And usually when you start digging down into it and do some asks around it, you find out that the maintenance work is not really that much fun. And so the best developers want to be building the new stuff, and they don't want to spend time on maintenance. And so then it's generally like the new developers or some of the maybe junior developers, get stuck doing this dirty work, as they often call it, of doing the maintenance and fixes on things. And it really comes down to just the fact that this maintenance work can be really, really annoying. And that's something that we need to tackle. And we can just, a lot of places will just say, nope, maintenance is everybody's job, bugs is everybody's job. If you build it, you're going to fix it, you're going to take care of it. And so just deal with it and figure out how to do it. And a lot of places, that's a great way to do it. One of the things I started doing with my teams, especially because I was one of these developers who was stuck maintaining my own code and just saw how annoying it is. And I used the typical developer sort of guiding principle of laziness of how could I make my life better? How can I make my life easier? And so I really set out to figure out what was it that was so difficult about maintaining an application, and is there anything we could do at the beginning of the project to make that be a little bit easier, make that be a little bit smoother? And the source of this frustration really comes down to a thing that we're probably all very familiar with right now: technical debt. And the solution to this is moving to a thing called, or that's been sort of coined as called technical health. If we can reframe how we're thinking about our applications and how we're building our technical debt and start thinking about the future and building the technical health, we can really change the picture of how we build applications as well as build in for maintenance in the future. So to first make sure we're on the same page and set some definitions for this stuff, technical debt was a term that was coined by Ward Cunningham. So he's been around the Agile world for a while. He invented the idea of the wiki. So of course, most people know Wikipedia now. And so if you can think far enough back before there ever was a wiki, that's when Ward Cunningham started putting these ideas together. And he also coined this idea of really looking at, once we ship code, we're trying to get it out the door fast. Sometimes we make some choices that are not going to be great in the long run, but we sort of take that hit, we take that cost right now, and we promise ourselves we're going to come back in the future and rewrite it and refactor it. But the problem occurs if your debt is not repaid. So we can tack on new problems on top of the old problems, and eventually this can be a really difficult problem to overcome, and it's so difficult and takes so much time that we never actually do it. So instead, we need to really be thinking about our engineering from the very beginning, from the ground up, using new ideas, well, they're not so new anymore, but the object-oriented kind of ideas, using a bunch of other techniques, which I'm going to talk about in this webinar here today, that will help us to get ahead of technical debt and to do that refactoring as quickly as possible. Now, this idea of technical health, you may not have heard yet, and that I heard it from Declan Whalen. He did a presentation at the Agile 2018 conference, and a whole, I think it's actually a 4-hour salon on how we can rethink technical debt in the way of technical health and design systems from the very beginning to be healthy. So I want to make sure I give some credit to Declan Whalen for this concept and where it came from. And he was really driving this idea of could we architect for moving to zero defects? And that requires this thing called system thinking. So system thinking, as with many things, Edwards Deming said this really well. Deming, if you're not familiar with, is the guy who helped Toyota with their Toyota production system. And so all of the Agile is built on Lean. Lean comes from thinking of Taiichi Ono over at Toyota. And he got, a lot of his ideas from Deming and working with Deming post-World War II when they readapted and rebuilt their factories in the best, most optimal way possible. And a couple of the sayings that Deming is known for are up here on the screen: that a bad system will beat a good person every single time. And also that your system is perfectly designed to get the result that it does. So if it's really hard to debug your application, it's because your application was designed to be really hard to debug. So if you want to get to a system that's really easy to debug, the only solution is to design an application that's easy to debug. So easier said than done, but that's why we're here today. So this is also the same foundation that gave us the idea of sort of minimum viable products. If we do this system thinking, it changes the way we're looking at things. We're looking at the entire product. We're looking at the entire thing. And we are breaking it down into pieces, and we may not build the entire application up front. We may build just a few features and deploy those out to the world, and then come back later and add more pieces onto it, and then build on top of that and build on top of that. As you can imagine, this is even more complicating some of those architectural decisions. So if you get some technical debt in that first MVP, and then you don't fix it right away, and you add on more pieces and add on more pieces, this approach to MVPs can actually start to make work a little bit more difficult and make your architectures a lot more difficult if you're not thinking about the future use and the future maintainability of this. So speaking of the future, and maybe because I grew up in the 80s, the Back to the Future really sticks in my mind and is the way I sort of framed this for my teams when I was working on this, like a good, well, let's just say 10 years ago, probably a little bit more than that. But what I would ask my teams to do is sit down and imagine yourself 10 years off into the future. So imagine you've got this application, and we plan to not, maybe we're not planning for this application to still be around in 10 years, but things don't always go as planned. And I know when I was doing a lot of development work, I was coming in and refactoring and rebuilding applications that had been around for at least 10 years, some of them 15, 20 years, and a couple of them had been there for 30, 40 years, still chugging along. And those developers back then and 40 years ago had no clue and no desire for the applications that they built to still be in place 40 years in the future. But I think that it's a good challenge to put to ourselves to just think about this. Imagine, what if your application was not retired and not replaced, and somebody in the future has to come through and debug and develop your application? So imagine you're this new developer that's 10 years off into the future. You've been given a bug to fix, and you've been given a steps to reproduce, hopefully, and you need to go find the source of the error and fix it. So this mental exercise that you go through and figuring out how to do that in the best and most optimal way really helps you to design these applications with backwards traceability. And what I found is it required a very different architecture than we were traditionally building and we were traditionally putting together. And so I want to share a little bit with you about that kind of architecture and about the components that I ended up crafting with my teams and baking into the software to allow us to do this. All right. There is a thing out there called site reliability engineering. This might be another topic you'd be interested in. They've been driving towards some of the same ideas that once it gets out there, how reliable is it? How fast can you get things back on scale? And they've got a few ideas, and we're not going to talk in great detail about it, but it's not a bad technique to be aware of. So you can do a search for site reliability engineering. And as the guy who did it describes it, he said, SRE is what happens when you ask a software engineer to design an operations function. And so what they came up with this idea of an error budget. And so we make this goal that we want to have 99.9% uptime. And so if we reverse engineer that, then that means that we can only have 43 minutes of downtime per month. And so for each outage that goes, then we have to basically force ourselves to make changes, and each month that pull away from that 43 minutes, and we have to keep forcing ourselves to get faster and faster and faster so that we can maintain our uptime. But let's move past this a little bit, and let's look at a test case. If we're looking at some technical debt and we want to try to solve some of this stuff, you can use a technique called 5 whys to sort of drill down at the exercise and try to come up with some of these information. So, for example, if we have an application and delivery of new features is slow, we can ask ourselves why. And so if this is like 40-year-old application, usually the reason comes down to COBOL code. And we ask ourselves, well, why are we still using COBOL code? Well, it's because to replace that has been a really onerous effort. It's going to take years to do. It's not something that we can do really, really fast. All right, so why is it that we can't do it very fast? Well, the reason is because we can't replace it all at once. Why can't we do that? Well, the code is tightly coupled. We were just designing it for COBOL. Everything's working together. And so why is it tightly coupled is another good, now we're down to our 4th why. Well, because the decision logic was written into COBOL. So then we can ask ourselves a question there and say, well, why is that the case? Or is there something we can do about that? It made sense at the time, but we're in a new place right now. And could we restructure this? So by drilling down into this kind of 5 whys and looking at where we got to where we are, we can start to come up with possible solutions for this. So we would kind of work backwards from this. We know we need to make a refactoring, and if we can do some refactoring of the COBOL code, maybe we can make some new decisions, but maybe we can minimize that refactoring, just refactor a few things. So one of the things perhaps, if decision logic is, the tightly coupled decision logic is the problem, maybe we can move some of that decision making to the database. We can have the code that makes the decision and then stores the results of that into a database instead of storing that into COBOL code. And now another application can access that database, find out what that decision point is, and be able to react off of it. And then from here, you maybe can then now introduce a Java facade to the COBOL code. And this is a strategy that a lot of places are using. And so that facade then sits in front and creates a front end with the new technology, and the requests from the server go to the Java code. And the Java code, all it does in the background is call a piece of COBOL code. And if you've refactored the decision data to go to the database, what you can do is then progressively replace pieces of the COBOL code at those points where it writes to and from the database. So we can have, say we have 5 pieces of COBOL code and 5 points that it interacts with the database. We can let 4 of them run and pick one of them and let the COBOL code do its 4 parts and then put an answer into the database, and then the Java code goes to the database, gets the data that it needs, and then runs Java code to fill in the 5th piece. And then we slowly work our way backwards or piece by piece until we've gradually replaced all 5 pieces of COBOL code with 5 pieces of Java code, and now we can completely retire the COBOL system. That's one strategy that we could use. And then because we're in Java, now we can also add new things that we know that we want to add, like API functions. And so we can have an API that calls Java code, and the Java code calls COBOL code. So we can still have modern architecture inside of a world that works on COBOL. And by doing just a little bit of refactoring, which is basically the difference of making a decision in COBOL and then storing the result of that decision in a database instead of storing that result in a COBOL variable itself. So to solve that last piece of this, it may require hiring maybe more COBOL people to do that refactor for a short period of time, or maybe you need to hire a Java architect or coders to replace this. So just gives us some ideas of things that we can do. But we can also change the way that we actually structure the application, even if we're not dealing with COBOL applications, even if we're just dealing with modern applications. And so what I'm going to show you over here are four patterns that I discovered with my teams. And then we're going to get down to the underlying theory that drives all of this stuff. That was the big learning and takeaway that I had with my application. So the first one is this thing called HTML augmentation or object augmentation. And if you haven't heard of this phrase yet, the general philosophy is that if you're dealing with a web application, or even if you're dealing with some mobile applications, you can do this especially with hybrid mobile applications, the HTML becomes a great way to define an interface, and all of the HTML is done with these tags. And if you're thinking about debugging your application from the future and somebody gives you an error and says, hey, when you go to this page, people are getting an error, go figure out what's going on. The first thing you're obviously going to do is go to that page and pull it up and take a look at it. And as you go through the steps to reproduce, if you have them, then you're probably going to identify the error, and you're going to find out the error happens when I click on this button. So if you don't know how this application was built, if you're brand new, if you have no idea what the structure of this application is, you could spend hours and literally days, maybe even weeks, trying to hunt down the piece of the application that runs the code that gets clicked when this button gets clicked. So one of the things that we came up with, when we were working on this 10 years ago was, how could we put a clue into the HTML to tell us where to go in the code to find the answer, or to find, the thing that gets called or the action that happens when you do this. And so we came to this thing of like, well, if the button does all of these different functions, let's just put a class for this, or a link to where that code for the button is that handles the actions of the button that makes the button work into that HTML as an attribute variable. And when I was doing a bunch of these things, I was doing these things actually in Cold Fusion, if you can believe it, back when folks were mostly still using Cold Fusion. I know there's still some out there right now, but a lot of work has moved off of this. And Cold Fusion, if you don't know how that works, is you basically create custom tags. They look just like HTML tags, but it would be called CF button instead of. And so, it became a great way in Cold Fusion to be able to have that traceability in files. But when we moved out of Cold Fusion and over into other applications and Java applications and JavaScript applications, that was no longer an option for us. But we still did the same thing. We carried that concept over, and we used attributes to give us clues and pathways back to the files that we would need to update in order to debug this device or this part of the application. And so we have these sort of buttons, and you can add a class. And other people found out these same things as well. So for example, Google, you may notice that up here it says the class says MDC button. And MDC stands for Material Design, which is Google's design function. And so if they have a whole library of widgets and creations and things that you can do. And you can come into and just define an HTML button and then add this class of MDC button. And Google's JavaScript code will go through and turn it into a fancy button, one that moves and changes. So if it's an Android phone, then the button will show in the way that Android users are expecting to see buttons. And if it's an iOS phone that you're accessing from, then it'll show as a button in the way that iOS people are used to seeing buttons. And if you go to the web, it just shows as a standard HTML button. And you can add additional things like images as SVG graphics and all this fancy kind of stuff. And so this, if you haven't heard about HTML augmentation, I would definitely recommend going out and doing some research and look at some of these libraries like Material Design, and because it really helps to make your HTML object-oriented. And if you've been studying any software development for a while, object-oriented pretty much has taken over the world, and everybody is doing object-oriented programming. And it's the same idea. Let's create a thing and then a traceability from that thing to the code that's then required to execute on it. And then the extra benefits you get out of this is you have CSS, these style sheets that you can add into your application and they just take the existing HTML and make it look to match the design styles that you're looking for of your application. And in the future, if you ever wish to change an application, it actually makes it really, really fast and easy, because you can just remove the style sheet, design a new style sheet, and add it in, and now your existing HTML completely changes and to a new look and feel. You can even reflow things on the page and have them lay out in completely different ways just based off of the CSS. So separating out your design from your structure of your page is one of those design principles that we have definitely evolved towards. And if you're using this class MDC button, for example, and you decide that you want to change this from a button, a regular click button, to maybe a drop-down menu button that gives additional details, or maybe it mixes in an input box, and you can go into material design, and instead of using MDC-button, you can use something like MDC-dropdown. And you just come into the HTML and you just change that one piece of text, save it back to your server, and load it up in your browser, and boom, you've got a drop-down button instantly instead of a regular simple click button. So it's really fast and really powerful to be able to make really gigantic changes when you start using this augmentation approach. So some of the other advantages of HTML augmentation: anybody can write HTML because it's text-based. You don't have to really understand a lot of coding things to do this. And so I've been able to pass that off to designers, that can actually build entire front-end applications because they happen to know HTML as well. And they go to Google's website and they look up material design and like, ooh, I want that button. And then they just go look for that button, tag, go look for the class, they match it up with the material design name, they add it in, they load up the page, and it's like, yay, looks great, that's fantastic. And so they get this page entirely laid out exactly as they want it to look in real HTML code instead of in just graphic design files or PSD files. And then they can hand that off to a developer and say, make this work. And now the developer can add additional attributes that then tie into the code that's going to execute when you click on stuff, or when you submit a page, or you upload files, etc. And all of this becomes traceable. So we know where the design files are. We know where the code is just by going to the web page and doing view source, or maybe even right-clicking on the thing that's broken on the website and doing inspect, and a little pop-up tool for Google, or Google Tools, or whatever you use as your debugging tool. So it makes it really fast and really easy to do the traceability, and also to just completely swap out entire huge chunks of code around this thing. You also end up be able to get some built-in 508 accessibility if that's a thing that you need to do, because a lot of these libraries work in that same kind of way. Some other examples on here are Ionic and Kendo UI, which I would definitely recommend checking out. Now, when we start doing this stuff and we start making these things accessible, and we're starting to give those little cues as to where code exists on our server, now we also need to think about security, and we have to get much more secure. And so the next thing that we really tackled was, what is the best way to be secure? And we found that the best way is a thing called whitelist role-based security. And so what we did with our stuff is we started adding roles to our HTML tags. So if we had this button, and that button was only supposed to be visible to admins or editors. Let's say we're in a review kind of site. Then we would just add this tag that said roles equals admin/editor, this list of role types. If anybody was in one of these roles, that button showed up for them. If it wasn't in those roles, the button disappeared. We also got even more fancy. We started just doing roles true or false. So if you were not logged in, roles equals false. And so then we would show you the login page and the inputs, so that you would have this, text and password and the login button. But if you were logged in, then we would hide that from you. And instead, we might show you nothing or show you something else. But allowed us to give this real granular control over the user interface based on roles. And if later we decided that we needed to add a feature to a role or take a feature away, all we had to do was come into these tags and just remove that role from the attribute of that tag, and now that user would no longer be able to access that feature. Now, as you maybe can start to think about this, that doesn't mean it's necessarily secure, as we're just showing and hiding features. So we also need to think about role-based whitelist security on a server. So to define a little bit about what we mean by whitelist, this is in contrast to a blacklist. And in a blacklist, we make a list of people who are not allowed to access anything. The downside of a blacklist is, let's say we add a new role or we add somebody new to our user base, then we are not going to, then those people will by default get access to every feature until we go in and add them to a blacklist. And that can get us into real trouble. So whitelist flipped this on its head and said the default access for any feature that we build is no. You do not have access to this. So the only way you get access is if a developer, a coder on the back end goes in and adds access to that role for that feature. So that allows us to be so much more secure, and we're going to start from this place of security and nobody has permissions to anything. And so then we'll add permissions, role by role. And then the other thing we found out is once you started tying it to user accounts, it became really hard to debug. It was so onerous to go back, find all those different accounts. When somebody quit, then their account disappears. Then you have to go hunt down where their username was added. That is just too much work. So instead, if you always do a role and then assign people to those roles, you can delete that username from that role group, and it doesn't matter. You have no maintenance work to do. And as well, if you want to give people additional permissions, you just get the user account and add a role to that user account, and now automatically they have all the permissions that go with everything associated with that role. So it becomes a very quick way to set permissions on an application. But the last thing to think about role-based security is you must implement it on the server first. Then you can also implement it on the client side. So, for example, if we are going to have a application where we've got people who can upload content and a second set of people, a different role called editor that can then change and update that content, what your database has to do is every time you create a new piece of content, you first check and see if the user is logged in, and if the user is logged in, then you let them do an insert in the database. Then if people want to update, you then check their roles and see, does this user have update privileges? Are they assigned the role of editor? If not, you reject any update possibility. Now, if the HTML, if the front end of the application has a little update button for the user because there's a bug, and they submit it to the server is going to block it and not let them make any edits or updates. So you always do server first. Now, just doing server-side security can be really slow. For example, we have a list of errors by storing stuff in the database. Then we can, that's not a great usability for the front-end user, so we can go back and add front-end client, checks and say, for example, does the password have 12 characters or more? Does the password have any special characters or not? And all of that code has to be in the server. It can also be added to the client to be able to save things down and be able to give you that quick way of interacting with things. All right, so that's the first pillar here or second pillar there of whitelist security. So the third thing I want to talk about is RESTful designs and APIs. So we started discovering that not only was it great to look at objects on the HTML page, but we could also look at the URLs on our server and let that be a clue as to where to go in the code to find all of the pages to be able to maintain this section of the code. But we also discovered that in order to do this, you had to have your URL structured in the right way. And the funny thing about this is, as we started doing more research into the intent of REST APIs and REST designed URLs, we found out that the creators of REST actually had this same idea of object-oriented design when they built URLs, but we just started using RESTful API URLs incorrectly. So let me give you some examples of how we use REST URLs incorrectly. We might have a URL that says, here is an account, and we're now going to add new. So we're going to have a URL that says account.addNew. That's going to give us a page to enter in details and create a brand new account. Or let's say we have a credit card, and so we're going to have an account that adds funds to that credit card. And so then that gives us a page. We make the connection out to Stripe or something like that to authenticate against the credit card. Those are all things that we call event-based. So there's an event that happens, like we're adding something new, we're adding funds. That's an action, that's a verb that's happening. And that's event-based. But that's not how REST URLs were supposed to be created. REST URLs were supposed to deal with the object. They're supposed to deal with an account. And then there are all of these things called operations. And there's generally 4 different operations, or you can think of these as CRUD, create, read, update, delete. And there's a bunch of things that you can do on these URLs. So in other words, you can post a brand new thing to your account. So you can use the same URL of account and post an update. You can do an update to an account by using a verb that's called put. So you just use, instead of post accounts, you do put accounts. If you want to delete account, there's a verb called delete, and you just say delete account. So we don't actually need to build URLs with these verbs like add new or delete, or anytime you have a verb in your URL, you are not using REST URLs correctly. You're not using them the way it's designed. And what we discovered was you're actually making your application harder to maintain because you're creating URLs that are event-driven, not URLs that are object-oriented. You want object-oriented URLs. And when you start defining these using REST the way REST was intended to be, now all of a sudden everybody, you've joined the rest of the world that builds universally compatible APIs that follow the REST specification, and you can now make your APIs available to services like Zapier. And so there's a lot of applications out there that set up these API points, and anybody can connect to their API just by knowing what those objects are, for example, accounts or posts, and then I can add a post, I can update a post, I can delete a post, or I can add, update, or delete accounts through my API just by using the standard post, put, delete, get actions that are built inside of REST. So when we teach teams how to do RESTful design, we start to think about things from an object-oriented point of view. So instead of looking at an event-based URL, we say, all right, what is the actual object here, and what's the action that we're taking? So if we're going to add funds, well, really what we're looking at is for a particular account. So we're going to go to our accounts object. We're going to look for user number 37, and we're going to look for the funds object under user number 37, and we're going to use the post up function to be able to add additional funds into that thing. Likewise, if we're going to add new funds, but we're going to do it by credit card, we're going to use that as a URL variable. So we're still just, our URL is go to the accounts code on the server, find user 37, find their list of funds, and we're going to send you a type of credit, and here's the details on that. So we can look at things like itineraries. So we're always looking for a plural version of the object. So we're looking for a collection. So building good RESTful URL starts with a noun that represents a collection of objects. Then if you are going to access any one portion of or one object within that collection, then you might add a URL for its unique ID. If you're going to make changes or do queries against the entire collection, then you can just add things using URL variables. For example, this would be an airline example. So we want to look for itineraries for plane travel, and using our carrier of American Airlines. So we're going to do a GET call to the API provided by, let's say this is the Google or Kayak. So we're going to do a call to Kayak's API, getting itineraries with a carrier of American Airlines. There's also a bunch of other functions. So if you want to see if something even just exists on the server, there's an action already that exists called head. You can look up some details on that online. Likewise, instead of doing a save action against an object, instead we might do a put action, delete, etc. like that. And so I started noticing that there was this pattern that REST used that we sometimes use in object orientation that actually ends up being better and faster than event-driven programming. And it was this thing that ended up coining as property invocation programming. Because if you think about it, every event that happens in our code happens because somewhere a variable value gets changed. And so if we stop thinking about events and start thinking about what variable changes happen, then this can we can start listening to these variable changes. And this becomes an evolution of basically kind of 5 steps. I'm going to very quickly go through what led to event-driven programming in the first place, so that we can have that quick background. And so in the original days, we had what we call procedural code. It's just line by line, the computer just executed the lines in a row. And so if we needed to change anything, we had to do a find and replace and search for a bit of code in order to replace it with additional thing. And this caused a lot of problems with typos and not having the same change, the same edit happening in multiple places. So we came up with this idea of functions. So instead of just having lines of code, let's create little bits of code, and we can call this bit of code, and we can reuse that bit of code just by calling this function name. And so that reusability gave us a lot of flexibility. But if you are going to use a function in multiple places, then it became a question of where should you store it and where should this fit into our architecture. And if I update it in one place or in the wrong place, then I might screw up another part of our architecture. So object orientation built on top of this and said, well, let's group all our stuff together. So if we think about what are our objects and what are our collections. So for example, we have accounts or we have itineraries. Any function having to do with itineraries is a function that is grouped together with this object and this collection called itineraries. So then we started talking about things as all variables became properties on this object or this collection, and all methods or all functions became called methods of this object, ways that this object interacted with the world or you interacted with it. And then we came into a problem here where the future viability of this would not match. You could create new code in the future that doesn't match the original architecture, which of course goes back to our original idea of what we were looking at when I started this webinar here. So this sort of fragility of things in object-oriented caused problems. So instead, Java came up with this idea of Java Beans, this really kind of quick, fast way to be able to create functions around variables. So each time you had a variable to update, you could create a set of listeners that could pay attention to these variables and then start to perform functions whenever those variables updated. And so that became this idea of events. And so whenever you had an event, you could just broadcast an event and say, I'm about to do this thing. If you care about when I add things to my accounts, or if you care about when somebody's requesting a list of itineraries, then I'm going to let you know when that happens, and now you can run some code, your own custom code, in order to be able to now respond to these events. And this is all over JavaScript. This is all over the web. We're doing event-driven technology there. But that still created this problem of if the architect did not build an event that you want to listen to, you are out of luck. You have to go back into the code. You have to go discover and make modifications, do recompiles, do all kinds of different things in order to create a new event that you can now listen to then execute your code and do the things that you want to do. So Let me skip through these things. So property invocation tried to attack and solve this thing. And there's multiple different versions of it. So as I was saying, REST itself actually operates on this principle. So you have a collection or an object on a server or inside of a database. And each time you update any property on that, then you can make other things happen. You may have heard of a thing called data binding that's happening inside of a lot of the front-end libraries these days. Kendo UI is one of those examples. And in Kendo UI, you can set up a view, an HTML page. It's got some data in there, and each time somebody updates, something in that data, then just saving that new value into the object, then fires off a bunch of code. You can listen to any of those pieces of that code. Part of that process is sending it off to the database. Once it gets stored in the database, on the database, you can listen, and anytime the database is updated, you can execute a bunch of code. And so if you rethink your applications from this idea of objects, and anytime any property changes on an object, then I want to be able to execute functions on that. So this gives us a little bit of a future, almost foolproof usage in the future. Anytime we want to extend this in the future, it becomes really fast and really easy. And to really follow property invocation, you basically come down to two events. There's a get operations and set operations. And then every function in the world only exists in two forms. You either are filtering data or you are listening to data or properties. So for example, you don't directly access any values on an object. You always must call a function. In Java, we would say, object.getValue or object.setValue. In Pi programming, it's one function to rule them all. So you would just say get and then pass in the property name. And likewise, you would say set, pass in the property name, and then give the value that you want to assign to that property. So here's some examples of that. And then based off of that, you can then do additional actions. You've got other actions like remove, which are really just set value to null, for example. And so now you can create objects, and you can add things to objects, and you can update objects and whole collections of things. And now we get into the listeners. So if I'm doing a GET request and I want to add stuff to the results of the collection or to the property. For example, I want to return my name. Somebody asked for my name, but I want to show my name and my company name, or my name and my job title. Now I can string these things together and create this filter. I'm not editing the object. The name field still looks like the name field, or it still looks like the title field. I'm not editing the database. I don't want to change the data in any way. I just want to change the way that it is shown. So that's what a filter is. So every time you get information, you modify it before it gets sent back to the original request. And then a listener function says, all right, now we're updating a variable, but I do want to actually modify this object. So anytime this happens, I want to take an action. I want to run some code, and I may make additional changes to the object. So there's a bunch of ideas in here as far as listening to objects and different methods for doing this, for creating different types of functions. And I'm not going to go into a lot of details on what property invocation does. If you do some searching for property invocation, there's a library up on GitHub that has all of the definitions for this and has a web page that describes how all of this stuff works. But you get to this point where you create self-documenting code. And so what we started doing is having our architecture match our URLs and having our URLs match the objects that are on our HTML code, and then became really easy to map a URL, to map a page that had an error all the way back to the code that was being executed. And then the whitelist security became this other layer on top of it that made sure that none of this was insecure, and that we blocked every dangerous transaction at the source, at the database, just using client security to augment. And through all this process, I started finding these patterns and building these patterns all together, and it came up with this thing I call the degrees of maintenance theory. And this really then drove the definition of the architectures that I would use and my teams would use from this point on. And so to understand this idea of degrees of separation, we first have to understand object-oriented programming. So this idea that we have different objects that are talking to each other and all the variables and stuff are related. We also have to understand this idea of 6 degrees of separation. This was a term that was coined by a play. There was an experiment around this. There's this idea that that all people in the world are only connected by 6 degrees of separation. And you may have heard 6 Degrees of Kevin Bacon as a popular game that's played of people trying to figure out, since Kevin Bacon has been in a lot of different movies, you can trace any 2 actors through Kevin Bacon to each other based on the movies that they've been in. So like this actor's been into that movie with a person, that person's been in a movie with Kevin Bacon, and Kevin Bacon's been in a movie with the third person. And so you have this traceability between all actors in less than 6 degrees. So we can use that same idea of degrees of separation within our code and within our objects and think about this stuff. And the last piece that I want to toss in as we wrap this up is this idea of model view controller, which is some of the things we were talking about before, where, for example, you can create an HTML page and then a CSS file that does all of your design. And so the model represents all of the data that gets stored about that object. The view represents the design and how it looks to the user. And the controller is loosely everything else in between. And so if you think about all of these different objects that we're creating in object-oriented programming, and all of this information that's being passed back and forth between these objects, each step that information is passed from object to object is a potential point of maintenance. And so you can actually think about, if you've got a property that you need to add or change, and it's going to go through 5 different objects or 10 different objects to get there, if there's a bug with that property, you might have to look at 10 different files in order to be able to figure out where exactly that bug is. And I started noticing this tendency that if the bug was 1 degree of separation from the user input form, then I could make a really easy estimation of how long that task was going to be. But if it was 10 degrees of separation from that input form, my estimates that should have been a 15-minute bug could easily multiply. And so it created this equation that people started using of the maintenance time equals your estimate about how long you think this task is going to be, and then multiply by the number of objects that this data must pass through in order to get from the user to the database. And so this can help you to guide some of your design ideas and principles to minimize the number of handoffs between objects, to minimize the number of layers between this, and it actually can help you to speed up your ability to fix bugs and to deliver new architectures and applications by minimizing the number of steps. So one of the examples or exercises that I do with teams is to have them map this stuff out. So for example, here is an application that I was maintaining for a while, and the user interface had a front-end framework that was a JavaScript framework that captured data from the user. Then there was an HTML and CSS that made that look, to mock that all up to make it look according to design. Then there was also a Java class that generated the HTML and CSS that then communicated up with a REST server. The REST server itself had a Java application that was handling all of the REST calls. That controller had what they called an interface in Java, which defined the generic version of that REST interface. That interface itself had its own implementation code. That code then had its own post processor. You can start to see how many levels there were. That itself had a data access object, and then there was a implementation of that object on top of it. And so when we counted up all of these things, we started noticing this pattern of things that should have been a simple fix. We're just changing a field name. It should have been a matter of 15 minutes to get it done. 15 minutes times 10 is going to get us to over 2 hours. And so we started realizing that the reason that our estimates were wrong, the reason it took so long to debug what should have been a really simple thing, was because we had added so many layers that the code has to pass through in order to get from the user to the database. So you can minimize your maintenance time by shrinking the number of levels or the number of layers in your application. So a couple lessons learned here. Be careful of libraries. Libraries are good, but only use libraries if they are a huge savings in time. Otherwise, even simple find and replace can be easier to debug. Make sure that you are tracing your layers that you're building between different pieces of things, and ask yourself when you're doing JavaScript and objects or other object-oriented programming languages, do you need interfaces? Do you need these extra definitions? If you're only using an object once, don't use an interface because it's just making your life harder. So there's some functions that go into that and some exercises that tap into that. All right, so a lot of information there, and we're coming up to the end of our webinar time here. But hopefully you found these ideas interesting and useful. I'll stick around after 12:30 here, and if you have any questions that you want to ask or that any additional information you'd like to ask for, feel free to chime on in. Thank you for joining us today.